Hello friends, in today's lecture we shall be discussing about entropy change in liquids, solids and gases. Then we shall talk about reversible steady flow work relations and the Gibbs equations. The TdS relations. Recall that the quality delta Q upon T internally reversible corresponds to a differential change in the property entropy. The entropy change for a process then can be evaluated by integrating delta Q upon T along some imaginary internally reversible path between the actual end states. For isothermal internally reversible process, this integration is straightforward, but when the temperature varies during the process, we have to have a relation between delta Q and T to perform this integration. Finding such relations is what we intend to do in this section. The differential form of the conservation of energy equation for a closed stationary system containing a simple compressible substance can be expressed for an internally reversible process as delta Q internally reversible minus delta W internally reversible is equal to du, but delta Q internally reversible is equal to T ds. Delta Q internally reversible out is equal to PdV. Thus, T ds is equal to du plus PdV, or T ds is equal to du plus PdV. This equation is known as the first TdS or Gibbs equation. Notice that the only type of work interaction a simple compressible system may involve as it undergoes an internally reversible process is the boundary work. The second TdS equation is obtained by eliminating du from the Gibbs equation by using the definition of enthalpy as H is equal to U plus PV. Forming the differential, we get dH is equal to du plus dPV, which gives dH is equal to du plus PdV plus VdP. On rearrangement, we get du plus PdV is equal to dH minus VdP. Substituting this in the first TdS equation, TdS is equal to du plus PdV, we get TdS is equal to dH minus VdP. This is the second TdS equation. These two equations are extremely valuable since they relate entropy changes of a system to the change in other properties. The TdS relations are developed with an internally reversible process in mind, since the entropy change between two states must be evaluated along a reversible path. However, the results obtained are valid for both reversible and irreversible processes, since entropy is a property and the change in a property between two states is independent of the types of processes the system undergoes. These two equations are relations between the properties of a unit mass of a simple compressible system as it undergoes a change of state, and they are applicable whether the change occurs in a closed or an open system. Explicit relations for differential changes in entropy are obtained by solving for ds from TdS relation equation as ds is equal to du upon T plus PdV upon T. So, ds is equal to dH upon T plus VdP upon T. The entropy change during a process can be determined by integrating either of these equations between the initial and the final states. To perform these integrations, however, we must know the relationship between du or dH and the temperature, as well as the equation of state for the substance, such as the ideal gas equation of state PV is equal to RT. For substances for which such relations exist, the integration of TdS relation equation is straightforward. For other substances, we have to rely on tabulated data. Entropy change of incompressible substance. We know that liquids and solids can be approximated as incompressible substances since their specific volumes remain nearly constant during a process. Thus, dV is approximately equal to 0 for liquids and solids. Therefore, the first TdS equation for this case reduces to ds is equal to du upon T and is equal to C dt upon T, since Cp is equal to Cv and is equal to C, and du is equal to C dt for incompressible substances. Then the entropy change during a process is determined by integration of above relation as S2 minus S1 is equal to integral of Ct dt upon T from 1 to 2, which is approximately equal to C average into natural log of T2 by T1. Here C average is the average specific heat of the substance over the given temperature interval. Note that the entropy change of a truly incompressible substance depends on temperature only and is independent of pressure. This equation can be used to determine the entropy changes of solids and liquids with reasonable accuracy. However, for liquids that expand considerably with temperature, it may be necessary to consider the effects of volume change in calculations. This is especially the case when the temperature change is large. A relation for isentropic processes of liquids and solids is obtained by setting the entropy change relation equal to 0. It gives S2 minus S1 is equal to C average into natural log of T2 by T1. That is, the temperature of a truly incompressible substance remains constant during an isentropic process. Therefore, the isentropic process of an incompressible substance is also isothermal. This behavior is closely approximated by liquids and solids. The entropy change of ideal gases. An expression for the entropy change of an ideal gas can be obtained from any of the TdS relation equations by employing the property relations for ideal gases. By substituting du is equal to Cvtt and P is equal to RT over V into first TdS relation equation, the differential entropy change of an ideal gas becomes ds is equal to Cv dt upon T plus R into dV upon V. The entropy change for a process is obtained by integrating this relation between end states, that is S2 minus S1 is equal to integral of Cv into T dt upon T from 1 to 2 plus R into natural log of V2 upon V1. A second relation for the entropy change of an ideal gas is obtained in a similar manner by substituting dH is equal to Cp dt and V is equal to RT upon P into second TdS relation equation and integrating The result is S2 minus S1 is equal to integral of Cpt into dt upon t from 1 to 2 plus r into natural log of P2 upon P1. The specific heats of ideal gases, with the exception of monoatomic gases, depend on temperature, and the integrals in above equations cannot be performed unless the dependence of Cv and Cp on temperature is known. Even when the Cvt and the Cpt functions are available, performing long integrations every time entropy change is calculated is not practical. Then two reasonable choices are left: either perform these integrations by simply assuming constant specific heats, or evaluate those integrals once and tabulate the results. Reversible steady flow work. The work done during a process depends on the path followed as well as on the properties at the end state. Recall that reversible or quasi-equilibrium moving boundary work associated with closed systems is expressed in terms of the fluid properties as Wb is equal to integral of P dV from 1 to 2. We learnt that the quasi-equilibrium work interactions lead to the maximum work output for work producing devices and the minimum work input for work consuming devices. Taking the positive direction of work to be from the system, the energy balance for a steady flow device undergoing an internally reversible process can be expressed in differential form as delta Q reversible minus delta W reversible is equal to dH plus dKe plus dPe, but delta Q reversible is equal to TdS and TdS is equal to dH minus VdP, which gives delta Q reversible equal to dH minus VdP. Substituting this into the relation above and cancelling dH yields minus delta W reversible is equal to VdP plus dKe plus dPe. Integrating this, we find W reversible is equal to minus integral of V dP minus delta Ke minus delta Pe from 1 to 2. When the changes in kinetic and potential energies are negligible, this equation reduces to W reversible is equal to minus integral of V dP from 1 to 2. These two equations are relations for the reversible work output associated with an internally reversible process in a steady flow device. They will give a negative result when work is done on the system. To avoid the negative sign, equation 1 can be written for work input to steady flow devices such as compressors and pumps as W reversible internally is equal to integral of VdP plus delta Ke plus delta Pe from 1 to 2. Relations for the reversible work output associated with an internally reversible process in a steady flow device has far-reaching implications in engineering regarding devices that produce or consume work steadily, such as turbines, compressors and pumps. It is obvious from this equation that the reversible steady flow work is closely associated with the specific volume of the fluid flowing through the device. The larger the specific volume, the larger the reversible work produced or consumed by the steady flow device. This conclusion is equally valid for actual steady flow devices. Therefore, every effort should be made to keep the specific volume of a fluid as small as possible during a compression process to minimize the work input and as large as possible during an expansion process to maximize the work output. Example: in steam or gas power plants, the pressure rise in the pump or compressor is equal to the pressure drop in the turbine if we disregard the pressure losses in various other components. In steam power plants, the pump handles liquid which has a very small specific volume, and the turbine handles vapor whose specific volume is many times larger. Therefore, the work output of the turbine is much larger than the work input to the pump. This is one of the reasons for the widespread use of steam power plants in electric power generation. In gas power plants, the working fluid, typically air, is compressed in the gas phase, and a considerable portion of the work output of the turbine is consumed by the compressor. As a result, a gas power plant delivers less net work per unit mass of the working fluid. Minimizing the compressor work. We have learned that the work input to a compressor is minimized when the compression process is executed in an internally reversible manner. When the changes in kinetic and potential energies are negligible, the compressor work is given by W reversible in is equal to integral of VdP from 1 to 2. Obviously, one way of minimizing the compressor work is to approximate an internally reversible process as much as possible by minimizing the irreversibilities such as friction and turbulence. The extent to which this can be accomplished is limited by economic considerations. A second and more practical way of reducing the compressor work is to keep the specific volume of the gas as small as possible during the compression process. This is done by maintaining the temperature of the gas as low as possible during compression, since the specific volume of a gas is proportional to temperature. Therefore, reducing the work input to a compressor requires that the gas be cooled as it is compressed. To have a better understanding of the effect of cooling during the compression process, we compare the work input requirements for three kinds of processes, that is, an isentropic process involving no cooling, a polytropic process involves some cooling, and an isothermal process involves maximum cooling. Assuming all three processes are executed between the same pressure levels in an internally reversible manner and the gas behaves as an ideal gas with constant specific heats, we see that the compression work is determined by performing the integration in this equation for each case with the results as shown here. For isentropic, W at compressor in is equal to Kr into T2 minus T1 divided by K minus 1. For polytropic, W at compressor in is equal to Nr into T2 minus T1 divided by N minus 1. And for isothermal, W at compressor in is equal to RT into natural log of P2 divided by P1. The three processes are plotted on a PV diagram for the same inlet state and exit pressure. On a PV diagram, the area to the left of the process curve is the integral of VdP. Thus, it is a measure of the steady flow compression work. It is interesting to observe from this diagram that out of the three internally reversible cases considered, the adiabatic compression requires the maximum work and the isothermal compression requires the minimum. The work input requirement for the polytropic case is between these two and decreases as the polytropic exponent N is decreased by increasing the heat rejection during the compression process. If sufficient heat is removed, the value of N approaches unity and the process becomes isothermal. One common way of cooling the gas during compression is to use cooling jackets around the casing of the compressors. So friends, here we come to the end of our discussion and therefore we sum up. The two TDS equations are extremely valuable since they relate entropy changes of a system to the changes in other properties. The work done during a steady flow process is proportional to the specific volume. Most steady flow devices operate under adiabatic conditions, and the ideal processes for these devices is the isentropic process. So that is it for today. In the next lecture, we shall be discussing about Maxwell relations. Thank you very much.